Okay, good afternoon. How you doing? Yeah? Thank you for your patience as I'm getting set up here. It's good to be back. Administratively, I sent out an email or a message. Any questions about what's coming up? Okay, so we have an exam on the 24th of February, and you can bring a sheet of handwritten notes, writing on both sides, and it'll be in this room. Okay. There should be another in-class assignment that just became available that would be due tonight, and then we have another assignment that will be due before we meet on Tuesday. Well, let's go ahead and get started. The last time we met, we discussed a little bit on, that's not right. Well, it was a review of stress and strain, but it was really not that. It was really discussing material properties. Okay. And then today we'll continue talking about material properties. We'll talk about ductility a little bit more, a couple of simplified material models, linearly elastic, perfectly plastic, and linearly elastic, linearly plastic, strain hardening. We'll talk about modulus of resilience, modulus of toughness, Poisson's ratio, and then we'll go into a general approach that we might take when we're attempting to attack these problems in mechanics. Okay? The notes, do you have the notes? Were they online for you to download? Yes? Okay. And CoLab should be there as well. And I'm not getting any complaints about audio, so I think we should be good. Okay. So the last time we met, we discussed tensile and compressive tests. We discussed stress-strain relationships, the elastic modulus, which is the Young's modulus, which is related to Hooke's law, and we also discussed yielding. Okay. And we began to look at a little more detail, or look at stress-strain curves in a little bit more detail, and identifying kind of the linear regions, proportional limits, elastic limits, and or elastic limits, proportional limits. I mean, these guys, the yield, and here they don't, but often the yield strength, the proportional limit, the elastic limit, they all get lumped together. In this particular source, they call this the true elastic limit, way down there. And then we discussed briefly, and we'll do this again in a second, about the 0.2% offset method for calculating out the yield strength. We discussed elastic moduli, and the two big ones that we want to remember, I mean, there were a number on a slide with wood and polymers and rubber and steel and aluminum, but the two big ones for this class that we want to keep in mind are the elastic moduli of steel and elastic moduli or elastic moduli of steels, which are. We also discussed residual strain, and just as a so residual strain, right? And we'll do some more on this today, where you can go up past the yield strength of the material, but when you come back down along a line with the slope of the elastic modulus, you aren't going to get back to where you started, right? We don't spring back all the way to our initial state of zero strain. And then the 0.2% offset method for yield strength. Okay, so this is more appropriate for ductile materials without a clear yield point. So we saw one of those stress strain curves for like low carbon steel, and it kind of had like a whoop, and it came back down like a little plateau, and then it started to strain harden. In that case, it's pretty clear where the yield strength or where that yield point is. Okay, it's at that sharp point. But there are a lot of ductile materials, such as the alloys of aluminum, that don't have a very clear yield point. So in that case, we can use this 0.2% offset rule, where we look at going on the x-axis 0.2%, and then we draw a line that's parallel to this linear region, right? And with elastic modulus as the slope. And then we see where does it hit the stress strain curve, and where does this new offset line hit the stress strain curve, and that's what we call the estimated yield strength. Okay. Now, do you think maybe it should be over here because it's kind of yielding? Or do you think it should be over here? A little bit debatable, right? But there is a lot of uncertainty when you do these experiments. You do one sample and it shows a yield strength of one value. You do another sample, you show a yield strength of another value. And you get agreement and you get a number. Okay? But it's kind of like telling everybody that your temperature is going to be exactly 98.6 degrees Fahrenheit. Okay? There's some variability there. So for the purposes of design, we want to not be operating right on the margins unless we have to, unless it's a very expensive application like sending a rocket up into space where you want to have minimal weight. Then you do operate closer to the margins, and then you do more testing, and you also make sure that your materials are meeting a higher standard of quality, because a lot of this is dependent on the processing and the manufacturing of the materials, right? The heat treatment, the purity of the alloy itself. Many parameters go into how much variability you're going to have in the elastic modulus, in the yield strength. Okay, but this is a technique for estimating the yield strength. All right, so that's kind of a little bit of a longer review than normal, but that's what we discussed last time, and it was a little bit rushed at the end. So I wanted to cover that. Now, let's go back and briefly discuss ductility. We have a sense of what this is. We realize that a ductile material is one that's going to not break immediately. We talked about the ceramics, we talked about glasses, how those are brittle materials and they just kind of have a catastrophic failure. A ductile material, it's going to get to its yield and then it's going to go for a little bit. So another way to think about this is a material that can absorb some amount of energy, okay? Because it's kind of like a spring, right? We talked about bars before. And this is kind of like a spring that's going to let you uncoil it a little bit before it finally breaks, as opposed to a spring made out of very brittle material that just snaps. Now, in the engineering world, there are kind of two ways to report ductility, and I think the engineering community kind of agrees that these are not the best ways to do it, but these are ways to do it, okay? And one is to think about what is the percent elongation. Yes? I do not know. I think we are, because it says there are people there. If there's no video or if there's no audio, that's something I can try to correct, but I think we are. I'm sorry to that person. But if someone else sends something in the group me saying, hey, you're not streaming, please go ahead and do so now, because then, yeah, we'll have more than one account. Thank you for interrupting. So, yes, okay, two ways to report ductility. One is based on the elongation until break. Okay, so that kind of makes sense, right? We have these samples, they keep going, they keep going, they keep going, like a rubber band, okay, and then eventually snaps. Another way is to look at a reduction in the cross-sectional area at fracture. Okay, so what happens in this case is your material has kept elongating, and it gets narrower and narrower in that necking region, and then you take a cross-sectional measurement of that break and compare it to the initial cross-sectional area, and we get an idea of how much ductility the material might have had. Essentially, the larger the change in the area, okay, the larger the reduction would correlate to having a higher ductility. Something that's very brittle, it's just going to snap, and the cross-sectional area is not really going to change that much. So if we're interested in thinking about the first method, okay, the percent elongation, okay, what we can look at essentially is what is the strain at the break. All right, that's pretty much it, right? This is the final minus the initial over the initial times 100%, or it doesn't have to be times 100%, right? It could just be its units. It could be in microstrain. It could be in a fraction. Okay, but that's kind of one metric for measuring percent elongation. And then the other technique is here to take a look and say, okay, how much did the cross-sectional area change? I know that's kind of my, there you go, right? So initially we had some type of cross-sectional area, okay, like maybe out here, you know, obviously don't use this region because that's where it's gripped, or that's where it's mounted. And when it broke, it kind of elongated a little bit. You see this kind of necking occurring here, and then we measure that final cross-sectional area, and we're able to get a metric. You can see the necking in these aluminum samples. These are aluminum alloys. And then you can also see the lack of brittle fail, or the lack of necking and brittle failure in these samples. They're both metals, okay? And in fact, this is cast iron, okay? It's not, so cast iron actually has a high amount of carbon in it, okay? So to be a steel, you need to have less than 0.2% carbon. Cast iron, although it's just as it's iron, it's actually got more carbon than your standard steels do. And when you add that extra carbon, it becomes that rough surface, and the brittly fracture is something that we would expect. Okay, so that's a little bit on ductility. Now, I think it's neat to come up with some simplified models that describe the main characteristics of stress-strain curves and also allow us to make important calculations, or useful calculations, probably better said. So two of these simplified material models are the linear elastic, perfectly plastic model, and the linear elastic, linearly plastic strain hardening model. Okay. So the linear elastic, perfectly plastic model is simplified, and it captures the elastic modulus. Okay, so you see there's still this slopey region, this linear region that is elastic. So you know we go up and down that, we get back to zero strain, and it also captures the yield strength. And with those two parameters, you can create this model. This line may not, since I drew it, it may not look completely flat, but the point is it's supposed to be flat. It's a horizontal line. What do you think that means? I think, did I ask this question last time? I'm forgetting. I have a forgetful head sometimes. But what does it mean if we get onto this flat region? What does it mean? What's happening in terms of, yes?
Is it
Okay, so yes, we have good. So first we do have permanent deformation. Okay, so if we're out here, we cannot come back easily to this origin 0, 0. Okay. And then physically, what does it kind of mean? I mean, if you just interpret what the graph says, you get strain, and do you have to increase the amount of stress you put into the material? No, it just that's kind of dangerous, right? It just kind of coasts. Essentially says if once you get to that plastic region and you're applying a certain amount of stress, you're just gonna go until you break, okay? And yeah, another thing that would probably be nice to put on a linear elastic, perfectly plastic model is when it fractures, but that's not a necessity, okay, for much of what we do. So like it's nice to have what the percent elongation is when it ultimately fractures. But those are the two main things. What it does not capture, okay, are an ultimate tensile strength and strain hardening. Now it can capture certain amounts. It can still. It does capture, okay, residual strain from unloading, but what we're talking about strain hardening is a little bit different. And the other model that I said has plastic strain hardening in it does capture the strain hardening mechanism. Okay. So remember when we say strain hardening, right? Like you said, oh, if you go up, right? Like if you were to come up into this region and you're yielding and then you come back down, right? You have some residual strain and you have to go even farther up, like your practical yield strength has gone up to some point up here. Okay. I'll be more clear in a second when we look at linear elastic, perfectly plastic. But this model is still useful for thinking about the residual strain from unloading. Okay. And when you take the design mechanical components, you'll start to look at how the geometry permanently deforms with embedding of residual stresses and residual strains. But we're not gonna cover that except in the axial case. If I stretch a bar beyond its yield, it's going to not go back to its original length. And we can calculate that, and we'll show that. Linearly elastic, linearly plastic. Another simplified model. And what does it capture? Well, it's going to capture the elastic modulus still. It's going to capture the yield strength, right there. And then it's going to do something that's a little bit interesting. It's going to not go perfectly flat here, but it's going to have some slope. And what does this look like? This looks like that strain hardening region, right? Where it's kind of going up to get to the ultimate tensile strength, and then it comes back down once it's begun to neck and once it's hit the ultimate tensile strength. So it still doesn't capture the ultimate tensile strength, but it does capture a linearly increasing stress in the strain hardening region and during plastic deformation. And it still also can help us get an idea of what the residual strain from unloading might be. Now, is one of these models better than the other? I mean, it depends on what you consider in terms of utility. If your material doesn't have much slope to it, right? It also depends on which material you're using, right? If it's a brittle material, you're probably not going to care about these that much. Okay, you're just going to go boom, and that's it. Okay, you're broken. But if it's a material that is kind of like aluminum, and you can fit a nice little piecewise system with two lines to it, either one flat or one not, and the other one with a slope of E, then yeah, they can be quite helpful and quite friendly. Okay, so let's do an example. And this example you can also look on Colab, at least the math is there. So let's assume we have a linear elastic, perfectly plastic material with an elastic modulus of 210 gigapascals and a yield strength of 200 megapascals. If we strain the material to 0.3%, what will be the residual strain when the load is released? And notice, like I did this on the two questions we have for the in-class assignment. It's all words. All right, just all words. Some problems can be solved that way. And based on kind of, this is really great. Thank you for letting me be part of the group meet. I can't answer all the questions, okay? And I'm glad that you guys are like, do, right? I am getting, though, a sense that there needs to be some critical, slow reading, okay, of these questions. Like, people are saying, oh, the strain is, I don't know, 2%. I'm like, oh, no, it's not 2%, right? It's like 0.2%. It's a factor of 10. It's a big difference, right? And that's not to single, not, I don't remember who said that, okay? But I'm just like, we had to read these questions very slowly sometimes. They're not that many words, okay? Not that many words. It's not like reading a novel. So get every detail, get every unit in there. I'm also seeing when people are sending their snapshots, I'm seeing, number divided by number, and I'm like, where are the units? And then people are saying it's not working out. I'm like, okay, you gotta put, if it's not working out, I mean, I'm okay with, jumping right to the thing. If you get it right, you get it right, good. But if it's not working, slow it down, put in every unit, okay? Every one, and then make sure they cancel out. And I think if we take this approach, it will be less frustrating, okay? Now, I understand, it is frustrating. Do I make mistakes with my units? All the time, right? All the time. I have a little bit more experience, though, so I know that when I get, this is now, if I get a strain that's in 100% range, I'm like, okay, I screwed up, right? I just know that's not right. So yeah, let's keep going. By the exam, I think these difficulties will be ironed out. I hope. Okay, and if they aren't, send me an email, and I'm happy to chat about things. Slow it down, though. Slow it down. Okay, so here we have the model, which is just slope, flat line. And the linear region is just going to be Hooke's law, right? Where we have sigma is equal to E epsilon. And we can rewrite that as epsilon is equal to sigma over E. And what's happening here? So we say we are straining the material to 0.3%, okay? But in order to do that kind of large strain, right, we have to go up the elastic region. We actually don't know. I mean, it's possible we could give you a strain that's less, if we say, we're only straining, 0.001%. That's immediately okay, it's very unlikely that I'm going to be getting into a plastic regime, right? And that's a nasty problem from the person writing it who just wants me to say that the residual strain is 0, okay? Because I just go up and I come back down. This is not that kind of trick problem. We have strain at the onset of yield, so we get up to this point, and we know what it is here, but it would be nice to know what the associated strain is at the onset of yield, right? Because in order for this to have meaning, hitting a strain of 0.3%, right? We would like to know that, okay, we hit yield before we get there. So how do we calculate that out? We calculate it out by looking at what is this stress and what is the elastic modulus, okay? And we apply essentially just Hooke's law right there. So now we know that this epsilon, right, or this epsilon, okay, is just 0.095%. Okay. Any questions on that? Nice, right? So now what happens? So we get up to about 0.1%, right? It's 0.095%, but about, again, it's going to be hard to say exactly what that is. But we get to about 0.1%. We still have another 0.2% to go. Okay, so what happens? We go out to 0.3%. So we go another 0.2% and we get out to this point. So we've now loaded it as was specified, okay, to 0.3%. What will be the residual strain when the load is released? Okay, so now we got to release the load. So we're there, and okay, a little bit out of order. Okay, and we go back down. We go back down with the same slope as we had with the elastic modulus. This line, or these lines, are parallel to each other. And we don't have to recalculate out how far we went on the x-axis. We know because we went from the yield strength to 0. That's the same thing, right? So we're going to go the same distance, but just backwards, the 0.095%. So now, the last thing is, what's the residual strain? Well, the residual strain is going to be how much strain, okay, we've induced into the material by going through this process. And in this case, okay, we know we went all the way to 0.3%. We know that we came back 0.095%. So epsilon r is just going to be this max strain minus this strain associated with the onset of yield. Okay. So we have our residual strain is equal to epsilon max minus the strain associated with the onset of yield, and we get the answer of about 0.2 or 0.21%. Any questions on that? When we do a step-by-step, it's pretty straightforward, right? Pretty simple. Okay? But the problem probably sounds a little bit intimidating, especially the first time doing it. This shows one of the uses, though, of this linear elastic, perfectly plastic model. Okay? It gives us an ability to estimate what the permanent deformation might be in a material. And in this case, in a bar. Okay, if we go on, we're going to go on. Okay. So here's another example. Similar, but using a different material model. We're now going to use the linear elastic, linearly plastic strain hardening model. And we're going to say it has the same elastic modulus here. It has the same yield strength here, or here, okay? But we've added this strain hardening slope of 20 gigapascals. And note, these slopes are still in units of pressure, or pascals, or typically gigapascals, because the x-axis is unitless, right? This is dimensionless, so that this means that both the y-axis, the actual values I have on the y-axis, and the slopes are going to have the same units. We once again go to 0.3%, and now we want to know a few things, or a couple of things. What will be the residual strain when the load is released? Okay, and what will the new yield strength of the material be? Right. So we're able to capture the strain hardening behavior here. So we want to know essentially what did we peak at? What did we get to on the stress strain curve, and be able to then suggest that the next time you load this material, you have to go up to that peak again. So you've strain hardened, you've work hardened this sample. So here we go. This is identical to what we did the last time, where we calculate the strain at the onset of yield. That should, I thought I fixed that. I guess I did not. But anyway, this really should be, I mean, it just depends on what you're trying to do, right? But that's probably, it's better just to write it as sigma y. And then we go up to this new spot, and this is going to be associated with the 0.3% strain, right? All the way out here. Okay. And that's, we're going to call it our epsilon max. So we can see this will be the new strength that we're asking for, but to figure out what the residual strain is, we need to go back down. Okay, we need to come back down following the slope of this line and figure out where we're going to be here. But let's first, the new, okay, can be calculated essentially by saying, okay, let's put in like an imaginary new origin here. Okay, and I know that this is sy or sigma y. Okay, sy, sigma y, same thing, right? Same thing. And I have a slope. Okay, this is the s, the slope for this region. Okay, slope here, and I need a run, right, times the slope to give me a rise. Okay, so the run is going to be just this epsilon max minus the onset of the strain. Okay, so that's this x distance here, and that will give us kind of this new, right? This is a new additional, right? That new little bit. That's this. I don't know what we call it. Let's just call it the S newbie. Okay, so this is S newbie. All right. So when we do this calculation out, we get it's 241 megapascals. Is that higher than 200 megapascals? Yes. So it's probably a step in the right direction. Okay. It's not. You're like, is it a significant amount? I mean, I don't know. You know, it's less than 20%, right? But that's still something. That is still something. Okay, in terms of the strength. Now, to figure out the residual, we had to go back down down along the line. Now, we're actually going a further distance. Remember, we did this before. We did this before in the last problem, where when it came flat across, right, then we just came down. You can even see it right here. We would, if we had gotten to this point, right, with a linearly elastic, perfectly plastic material, and we followed the slope, right, we would be like ending up right around here instead. Okay, so we would have a different residual strain as a result. Okay, so what do we got to do here? Well, we got to figure out where this residual strain is. And so to do that, we're going to say, oh, it's just this epsilon max, okay, minus this distance, right? So this distance we can calculate. That's going to be the S nu, right? Not S newbie, but S nu divided by the elastic modulus, right? That will give us the run. We know the rise, now we need the run. So we subtract that, so we say this epsilon max minus this will give us this length right there. Okay. So we do that out, and we're careful with the units again, try to get ourselves into percentage. Okay. And then we've got a final answer. And you can see that, again, this is, there's Python code, you know, just to do this math if you like, available for your viewing pleasure. Any questions on this? It's kind of fun, right? It's kind of like multi-step process. You feel like you're doing something and we're calculating some, you know, it's not like a one-step kind of thing, right? So I think it's kind of fun. I was just thinking while I was here, I don't think I've done this before, but what if, and I don't have a, maybe I'll put a problem on the homework tonight for this. What would happen if you went compressive instead of tensile? I mean, we do this in DMC for sure. All right. If you go compressive, right, and it's a ductile material, then you can assume that the compressive yield strength, the compressive strength, that yield is going to be about the same as what you have with the regular tensile yield strength. Okay? And you can essentially draw these curves, but backwards, okay? Because you'd be going down. You'd be in quadrant 3, right? We're in quadrant 1 right now, but you would be in quadrant 3. Okay, so we've now gone through linear elastic, perfectly plastic materials, and linear elastic, linearly plastic strain hardening materials. Ductility. Let's move on to modulus of resilience, the modulus of toughness. And modulus of toughness and ductility are related to each other. And in fact, they can be a little bit confusing when you're thinking about, okay, what is what. I'll try to explain when we get to toughness how something could be tough, but not necessarily super ductile, okay? Even though we have those other metrics for ductility, right, with the percent elongation and the percent of change in cross-sectional area, okay? You could potentially have a material that's very tough, but still doesn't like neck, right, as much. And it'll become obvious when we look at the graph how that can happen. Okay, but first, let's talk about springs again. What do we see here? We see that if we have a spring, we can say F equals K delta. You're like, how many times are we going to see springs in this class? I hope a lot, actually, okay? Because I think it makes the abstractions simpler. Okay, so there are notes in the chat. Okay, I don't know. Okay, good. Thanks for checking my math. I think you checked it and it's okay, so that's good. All right. So okay. So where were we? Spring. Yes. I think they make our calculations of deformation simpler, and as we've seen before, right, they can also help us figure out what the internal loads are, because sometimes we have indeterminate problems where we do need the deformation. What's the energy stored in a spring? Well, you remember you can integrate under the curve, right? And that comes out to be 1/2 K delta squared for a linearly elastic spring. Okay. And another way, though, right? I mean, is to think, okay, it's just 1/2 whatever, it's a triangle, right? So it's 1/2 times base times height. Okay, so you could also think, oh, I got K delta here, and I have delta, and it's 1/2 times the product of those two. Or if you're in a situation where you're like, oh, I know what the force is when I get to where I am, and I know what my delta is, I don't even have to do K delta, I just do 1/2 force times delta, right? So lots of different ways to think about the energy. Strain energy, okay, so that's a spring. Let's think about an element experiencing strain. So here's a material element, and it's experiencing a normal stress, and the element has lengths of delta x, delta y, and delta z. Okay, so that it forms a volume, right? So if I want the volume, I multiply those three by the product of those three lengths, the lengths of those sides. If I want a cross-sectional area, for example, the cross-sectional area through which this normal stress is going, I'm going to be using just delta x and delta y. So here are some parameters. Cross-sectional area, like I said, it's just delta x, delta y, all right? And the force in the z direction, we can actually calculate. So we can, if you gave me the stress in that direction and I know the cross-sectional area, I can do the product of those two and I get force. And we can also calculate out the vertical displacement if I know the strain. So I didn't draw a strain on there, okay? But now we know that, okay, strain is equal to the change in length over the initial length, right? So if I have that strain and I have the initial length, I can get the change in length, as we see here. The energy, though, or the energy here, right, can be thought of, okay, and this energy is well, I guess let's think here. What are the units? All right, what are the units of energy? Well, the units of energy are Newton meters, okay, or joules, right? That's at least in the metric system, and we're still dealing with forces. So we have delta F, which is a force. And we're still dealing with displacements. Delta is a displacement, in some type of meters. So this is an energy. It's a delta W, but it's still an energy with units of joules. We have calculated the energy we're putting into this material element, okay? Or maybe it's a larger cross-sectional bar, whatever, or a larger piece of a bar. We can also think about what would be the internal energy and just say, hey, look, the energy that this material is absorbing in terms of potential energy, just like this spring, right? I had to put energy into the spring to get it to store that energy. Now we're saying the same thing about this material element. This material element is storing the energy that I've done work into, or I lost my sentence. I've put work into the material and it's stored in the material now. Okay. Look, there's a delta x, delta y, right? So this, we see where this came from, okay? This was, this is, the 1/2 is from there, okay? The delta f was the sigma delta a, the delta a was delta x, delta y, all right? Just showing that. And the d, all right, or the delta, sorry, is the epsilon delta z, okay? So that's right here. What do you think is going to happen? Delta x, delta y, delta z. That's equal to a volume, right? All right, that's equal to a volume. So now we have an internal energy, okay, which is still in terms of joules, equals 1/2 sigma epsilon delta v. Now, if I want an internal, or if I want an internal energy that does not depend on volume, right, like a specific strain energy, I can just divide by delta v, right? If I take this energy and I divide by that, I have like this new 1/2 sigma epsilon term. So what happens there? If this is copied, exactly what we had before. We have the strain energy on a given volume, and now we can say strain energy density, okay, per volume. That's like force per meter, or I didn't say that. It's joule per meter cubed, okay? Or Newton meter per meter cubed, or Newton per meter squared. And you're like, blast! How is this happening? We're getting to pressure again. Look, it's pressure again. It just keeps coming, right? Freddie Mercury and David Bowie would be happy. This is under pressure, all right? We're just going. So let's now remember Hooke's law. We're going to assume now we're in a linear elastic regime, okay? That we can apply Hooke's law. So sigma is equal to E epsilon. We rearrange that. Epsilon is equal to sigma over E. And now we can plop in the E, or the epsilons. Epsilons, E's, right? You know, not the same thing, obviously. Plug this in there, and now we have this interesting term for elastic strain energy density as equal to 1/2 sigma squared over E. What does this say? Well, it says if I put in more stress, I have more strain energy per volume, okay? What's interesting, right, is if my elastic modulus is higher, though, okay, I actually get less, strain energy density per volume. Okay, that's maybe a little bit interesting for a given amount of stress. Okay, so like a rubbery material, okay, if I can put the same amount of stress in a rubbery material and that thing stretches a lot, okay, it has a lower elastic modulus, so it's going to stretch more. Okay, that's actually going to be holding more strain energy density per volume than a material of the same dimensions, okay, or, well, let's be careful. This is dimensionless, okay? I have to be careful. It's dimensionless, right? I mean, it has dimensions of pressure, okay? But this is now saying I can tell you what the strain energy density is in a part of a structure, okay? I'm not looking at the whole bar and saying that's how much the bar is holding. I'm saying right there, if I know the stress and the strain, I can tell you. Or if I know the stress and I know the elastic modulus, I can tell you what the strain energy density is right there. Okay, so how does this relate to modulus of resilience? Pretty much directly. Okay, except we're going to the limit of the elastic regime. Okay, so what is this? This is the modulus of resilience. Okay, is essentially the strain energy density based on the proportional limit, meaning, or for our intents and purposes, usually the yield strength. So it says calculate out the maximum amount of strain energy that you can store per volume in your material, okay, based on its elastic modulus and based on its proportional limit, or in practical sense, the yield strength. So here's what it looks like. Very familiar looking, right? We had this relationship over here, 1/2 sigma epsilon. It's 1/2 sigma epsilon over again, except now we put in either the yield strength or the proportional limit for both of these, okay? Or you could say this is the yield stress or the yield strength here, and this is the strain associated with the yield, of the material, okay? So if we have a stress strain curve, something like this, and we're starting to go plastic, we go up, okay, to that point, and we say, okay, it's the area under this portion of the curve. And this is going, again, what are the units going to be? Wackio, the units again are pascals, okay, because this x-axis is dimensionless. All right, so, it's, if this were square, just be like, okay, this dimensionless value here times that height, but it's not a square, it's a triangle, so I take 1/2 of that. And it's going to have units of pressure. And as I said a couple of times already, we usually just use the yield strength, okay? And we've said this multiple times, it's difficult to distinguish between the elastic limit, the proportional limit, and the yield strength. So just use the yield strength. Any questions? Yes?
So the yield strength over the elastic modulus, does that make the resilience a function of whatever the elastic modulus Q?
I wouldn't say, no, not, okay. So I think what you're saying is, if I plug in sigma back into here and I have E epsilon, right?
Yeah.
Okay, well, then if I do that, right, I have E epsilon, or epsilon E squared, okay, so in that case,
Okay.
I'm going to have, I'll have, no, it's fine, it's an interesting point. You're going to have, now you're going to have the elastic modulus actually in the top, in the numerator, right? Okay, so back to that, I'm glad you brought that up because, we were saying before that it goes down with increases in elastic modulus when you're thinking about the stresses, but it actually goes up, okay, if you're thinking about it in terms of the strain. Okay, because like you just pointed out, you could write an expression where you plop this back in. Now you have epsilon squared times E. Right? Okay, so yeah. Okay, so yeah. It's interesting. You start, there are many different combinations of these equations that you can come up with. It's like V equals IR, right, in the electrical world. Okay, voltage is equal to current times resistance. You're like, oh, well, power is equal to, V squared over R. No, power is equal to IV. You can put all these different combinations out there. And that is kind of how mechanics of materials is a puzzle. And any of these classes really is, right? So if you like solving puzzles and you're stuck on a problem, just write, and that's when we get to the end today, I'll show you kind of this general approach. It's almost like doing that. Just put down all the equations and start seeing which ones, work, which ones apply, and we're puzzle solvers here. Okay? Sometimes you run into dead ends. So you have to back out and try something a little bit different. Okay, so that's modulus of resilience. What do you think modulus of toughness might be? Any ideas? We said it was related to ductility. I mean, you guys, I guess a lot of you have the notes, so you don't want to like just be appearing to be smart, although you are smart. Okay. But modulus of toughness has to do with the total strain energy. So, with fracture, I don't know what fracture is. Do you guys know what fracture is? We're going to look at the total area under the stress strain curve. And so now we have the modulus of resilience plus everything else. Okay, this other region over here. And as you might begin to see, this could be related to ductility. Okay, because remember, ductility was kind of one of the ways to measure ductility is how far you go, right? What was your percent elongation at fracture? So as you go more this way along the horizontal axis, you're going to have more ductility. Okay. But is it possible to have a very tough material that breaks like right here, but because it has a high slope and because it stays elastic for a long period of time, it actually is still tough, but it's kind of not very ductile because it doesn't get to very long percent long elongation? Yeah, maybe. I'm to be honest, I'm having trouble thinking of one. Okay, but well, glass. Okay, glass can be pretty tough. Okay, I mean it's brittle, right? But it can handle a lot of strain energy before it has a catastrophic failure. Okay. Yeah, that's a good one. Right. Gorilla Glass. Any questions? All right, we're good. Okay, so let's do an example. Let's say we have a linear elastic, perfectly plastic material with an elastic modulus of 210 gigapascals and a yield strength of 200 megapascals. If the material fractures or breaks at a strain of 0.3%, what are the modulus of resilience and modulus of toughness? Okay, so almost exactly the same wording as what we used before, but now we want to know what happens when the material breaks at 0.3% in terms of the modulus of toughness, and what's the modulus of resilience. Obviously, the modulus of resilience does not depend on the fracture, the strain of fracture. Okay, the modulus of resilience, right, is going to depend on the area under this portion of the curve. So these are all calculations that we did previously that can help us here, and we know that, okay, we're going to be going out to this strain of almost 0.1%. Okay. Oh, okay. And where are the values? Well, the values are not there because I did not. Sorry. I did them in okay. Oops. I don't want everyone looking at my files online. Hopefully there's nothing sensitive there. Here, this one. Okay, so this is example 6.3. All right, so sorry, I didn't put the answer in the slides, but they're in the collab. What do we do? For modulus of resilience, we just calculate this area here. Okay, so that's right here. I call it U sub R. And we see that it's really small, actually, isn't it? I think, oh, it's even more absurdly big. Okay, so we see that it's 1/2 times the yield strength, okay, times the strain associated with the yield strength. Okay. And it was in percentage, it was in percent, so I divided by 100 there, and yield strength was in megapascals, so I multiplied by a million. Okay, but then since we wanted it in, if we want it in kPa, all right, then I have to go from pascals to kilopascals, so I divide by 1,000. Okay, modulus of toughness is going to be this modulus of resilience plus now the rectangular portion. So epsilon max minus epsilon y, okay, times the yield strength. Okay, so epsilon, that's this region right here. Okay, so the UR, the modulus of resilience, I think it was around 95 kilopascals. And the modulus of toughness was like 540 kilopascals. It was just there and I can't remember. Oh, 504, 95 and 505. Okay. Great. Pretty straightforward, right? Since we're running low on time, we'll go through this one very quickly. It's the same as what we just did, okay? The modulus of resilience, okay, is not going to change here, okay? It's going to be the same. But what is different is that this region over here, okay, is a trapezoid. It's not a rectangle. So how do you figure out the trapezoid? Well, you know the height, and then you take the average of the top and the bottom. All right. So if you look in the code, that's what we did. That's what I did. Okay. For the modulus of, so we had to calculate a new, right? That new strength that we got up to, and we have to use 1/2 times the old yield strength plus the new yield strength. That gives us the average there, and then it times the distance between those two. And then yeah, there's a slight increase. So we have we went from 505 to 547 kilopascals. Great, straightforward. All right. So often a tough material is also a ductile one, all right, but it doesn't have to be. Oh, there and there I pasted it in. Okay, that was just for the second one. Okay, let's talk about Poisson's ratio in the remaining time that we have. So when you stretch a material in one axis, like you take a rubber band, you stretch it, what happens in the orthogonal axes? If you put me in like one of those stretching things, anyone watch The Princess Bride? Right. And like the guy, they're torturing him in the, no? No one here has watched The Princess Bride? Yeah, okay, all right. This is like 80s movie classic, all right? It's perfectly appropriate for your age group, okay? Perfectly appropriate for age group, okay? It's probably PG, okay? So anyway, there's this thing where they put the guy in a rack. And it's a comedy, all right? It's a comedy, all right, believe it or not. So anyway, so like, they put the guy in the rack and they're stretching him out, okay? And like saying, oh, he's like a certain amount dead or something like that. Anyway. If you stretch me out, do I get thinner or fatter? Right? I get thinner. Okay? I'm comfortable with my fatness, all right, but I would get thinner. I'm not going to do this, to get thinner. If I squish me, though, if you put me now in a compression, I'm going to get wider, potentially, okay, like a pancake eventually. So this ratio of how much you strain in one axis versus the amount of strain in the other axes is what the Poisson ratio is. Have you guys discussed this before in any of your classes? No. Okay. Yeah. This is an appropriate topic for this class. Good. That makes sense. This is mechanics of materials. Say, okay, so you've seen this before. You know what happens with rubber bands. And we know what happens in terms of longitudinal strain, okay? Because we've now done this, right? Multiplying. This is just me writing the same thing again. Sometimes I think it looks better when I write it. Sometimes it doesn't. Okay, and then this is a relationship. This is how much lateral strain there is. Now, what are we talking about? We're talking here about a change in radius. All right, so initially this cylindrical bar was green, and then it became kind of weird looking gray. Now that's just my drawing, okay? It went from this diameter and radius to a smaller, right? So here's diameter, here's radius, to a smaller one. That change in radius, okay, divided by the initial radius is a metric of strain. We're going to mess this up. I'm going to mess it up at least one more time before I die, okay? This ratio is the same as saying that the change in diameter divided by the initial diameter, okay, is a strain, okay? But don't take this distance, delta prime, and divide by the diameter, okay? Because it's delta prime on whatever, opposite sides, okay, of a cut, all right? So it's I get confused, okay? I get confused, okay? But this delta prime is the change in the radius, and the change in diameter is delta d, which is 2 times the change in the radius. You're like, duh, I got it, all right? But there are many times when I have to like draw a little picture in my mind, and I'm like, oh, radius, a little bit on this side, a little bit on this side, that's the diameter, right? And the change in diameter is going to be double the change in the radius. You're like, okay, really silly. But that's the beautiful thing about strain, right? It doesn't really care. This is a quantity that's dimensionless, okay? And you can say, oh, that strain's right there is that, okay? And whether I just gotta be careful that I calculate it correctly. It's either the delta R over R or the delta D over D, okay? But they're the same ratio. Now, what is the Poisson ratio? Poisson ratio for homogeneous, okay, isotropic material is the relationship of the latitudinal strain over longitudinal strain. So longitudinal strain is this one, and latitudinal is going to be this related to the change in the radius. Okay? And there's a negative sign. Okay, so when the Poisson ratio is positive, it corresponds to a contraction in the latitudinal direction with an extension in the longitudinal direction. And there's some good videos. At least, they're not. I didn't make them, but the ones that I posted from the Efficient Engineer and some of these others, they're pretty good. They explain this concept very nicely, and they even talk a little bit about the auxetics, okay, which are materials that have a negative Poisson ratio. Okay, so these are they're kind of engineered materials, right? So like little boxes put to each other that buckle, so that when you actually compress them, they don't expand. They actually kind of collapse a little bit. Okay, so the ratio is opposite of what you would see in a normal solid. What happens if you have a cube? Okay, well, here, again, we have to be careful with these ratios. Okay, see how they have a delta, the way they define delta L prime, all right, and the way we define delta L. So here, the change in length of this guy, it's delta L in this direction and delta L in this direction. So it's 2 delta L over L. So sometimes you have to be careful, and I kind of glossed over that. That's how we define it over here too. Because why don't we just attach this to a wall? Well, because we're trying to do this in a nice idealized method where everything can just move. right? If you pull on a bar that's attached to a wall, the wall is actually keeping the near the wall, right? So if I have this thing coming out near the wall, it's actually keeping the material from contracting, right? It's yes, it's applying a normal force that way, but it's actually applying a set of stresses to keep it from contracting. All right, so that's why we like have this thing in space, right, with a force on either end, because it allows both ends to freely change their dimensions. Okay, so we have delta L, we have delta L on that side, so 2 times delta L over the original L will give us the longitudinal strain, and the strain in the y direction, okay, you see this, is going to be this 2 delta L prime on either side divided by L, because this is a cube. Okay, so this length, the initial length was L as well. But you see now, this is interesting. Before we started with just, and this is typical, you start with cylinder and you say, okay, this is how much the radius changes, and it changes, in every dimension. But now if we have a cube, we see that there's an effect, right? If I pull in X, I see shrinkage in Y and Z. If I pull in Y, I see shrinkage in X and Z. If I pull in Z, I see shrinkage in X and Y. Okay? And that's all this is saying with these sets of equations. All right? And they come out to have a Poisson ratio of nu. Oh yeah, did I say that? That's how you say this. This is the Greek variable nu. All right. So, here is a cube. And now, let's say I have normal stresses, sigma x, sigma y, sigma z. Sigma x, sigma y, sigma z, and let's say this is the x direction, which is in line with the sigma x. I have normal strains that I can define in all 3 directions as well. I have Hooke's law. Hooke's law says that the longitudinal strain is going to be equal to the longitudinal stress divided by E. Poisson's ratio says the latitudinal strain is equal to minus nu times the longitudinal strain. Now look at what happens. Hooke's law tells me that if I apply stress in this direction, I get strain in that direction. Poisson's ratio tells me if I apply stress in this direction, I get contraction in the y direction. It also tells me that I get contraction in the z direction. Hooke's law, if I apply stress in the z direction, Poisson's ratio tells me that I get contraction in the wait for it. This is the x direction, yes, x3, okay? If I apply stress in the z direction, I get contraction in the y direction. And Hooke's law tells me I get extension in the z direction, okay? You see this pattern developing, right? And if you're bored on a Saturday night, I don't know what to do. I don't know how to do this one alone. Well, get some rubber bands, I guess. That's probably an easy way to do it. Get some rubber bands and pull on them. Okay. Okay, so the total, though, epsilon x, you see this? This is epsilon x1, epsilon x3, epsilon x2. I should have done it in fact, Hibbler's book does it the right way. This is fine. I just drew the z. This is just how I made them in Tinkercad. This is just Tinkercad, okay, guys? And so when I did this out, you can see that, or just add these stresses, add these strains to each other, okay? You add them up, and you're gonna get a total strain in the x direction. And you see that the total strain in the x direction is dependent on stresses in all 3 directions. And you can do that for the strain in the y direction and the strain in the z direction as well. So you get these relationships right here. Epsilon x, okay, is equal to, and this is essentially Hooke's law, 1 over E times the stresses, right? That's the Hooke's part. The Poisson part comes in on the two orthogonal axes, the y and z axes, if we're in the x direction. Any questions on this? Okay, we're almost done. And if you want to put it in kind of a matrix notation, okay, and you just want to write this down on your formula sheet instead, you can say that these strains are going to be equal to 1 over E times this 1 minus nu minus nu minus nu 1 minus nu minus nu minus nu 1 matrix, okay, with this column vector, sigma x, sigma y, sigma z. Okay, good. We don't have much time, but let me just go through the general approach, all right? And then you guys can look at the problems. They're not that, you know, I think they're well, you got the solutions here. They should be pretty straightforward, and you've got solutions in Colab as well. But let's just go through the general approach, and I try to use this general approach in the subsequent problems. You'll see it. If we're analyzing deformable bodies and mechanics and materials, here are 3 steps that Crandall, Dahl, and Lardner kind of suggest that you take. And these were the 3 steps that I was taught many years ago, and I don't always follow them. Okay, so you just go figure, right? But this is kind of a framework to do this. 1, look at the forces and equilibrium requirements. Okay, and we call that equilibrium. All right, so here, right, if we have this bar, it's got a force coming out of it, and it has a point A and a point B. It has an area A and this deformation in this direction, this axial direction. I can take a cut, and I can look at the reaction force. I mean, I can do both, right? I should look at the reaction force here, all right, if I'm being careful. I know it's equal to F. And then if I take a cut and I look at the internal force, right, I know it's equal to the external force applied. So I apply equilibrium. The next thing to do is look at geometric compatibility. Okay, and the final thing is force deformation relationships or constitutive equations. So when I'm looking at geometric compatibility, I can say, look, delta B right here, that's got to be equal to 0. It's not going anywhere. But over here, delta A is equal to the delta that's defined. All right, so I was just trying to write something down for geometric compatibility. There will be other problems where you really do have to focus on, we really do have to focus on geometric compatibility. All right, for example, the indeterminate problems, which we've done already. And then the last thing, write constitutive equations out. So now we have more than one constitutive equation, more than 2. We have these relationships, the Hooke's law. We know what stress is. We know what strain is. Right? And we also know what Poisson's ratio does. All right? So now we have a few equations that help us understand the relationships between the force and the deformation. So, you know, someone could say that, oh, maybe the sigma should go, you could put this one over here, like sigma equals F over A, because that's just going between force and stress, and there's no deformation involved there. Similarly, epsilon is equal to delta over L. That's just pure deformation. It's not a relationship to stress. Either way, if you want to put them over here under equilibrium, that's fine. All right? But if you're interested in trying to like get unstuck on a problem, just write 3 columns: equilibrium, compatibility, and constitutive equations. Put everything down together and start to do your puzzle solving. Okay? And that's what you have here. Thank you guys. I didn't quite get through everything, but you guys will be able to get through things okay without me. And we've covered a number of topics today: ductility, the simplified material models, resilience, toughness, Poisson's ratio, and a general approach to solving problems in mechanics and materials. I'll see you guys on Tuesday. There is an assignment due by midnight tonight and an assignment due by Tuesday at the start of class. Thanks.